anyways, this is a tutorial that was prepared by myself along with the people that I think here. And it is based on a signal processing magazine that we published last or 2 years ago, extending that. And the people who helped me to put together the slides were then with the University of Minnesota. They are now faculty members. Nikos Gatsis at the University of Texas, San Antonio, Vasilis Kekatos at Virginia Tech, Kim at the University of Maryland, and Hao Ju at the University of Illinois at Urbana-Champaign. So the theme of the talk, you can take different angles when looking at power systems, and the one I have chosen is the one that a systems engineer or signal processing guy can relate to. So the title reflects that. So I will start by some motivation. And everyone will admit that the grid is an aging infrastructure. A little bit of history never hurts. Both Bell and Edison discovered phone and light bulbs, and Tesla later on, the AC system, around the same time, 1800s. And fairly consistently, for the following 100 years, they evolved in a very similar way. They established monopolies, single commodity. We witnessed their growth during the 2 world wars. And then deregulation started around the same time. But if you look at the top, in the last 20 years or so, or 30 years, the grid is not too different. Okay, you have the Enron and some blackouts in 2000s, but the grid is more or less the same. But if you see how the DARPANET evolved over the years, you will agree with me that Mr. Bell would be really surprised to see where we are right now with the internet, whereas Edison and Tesla will feel at home with the grid. It didn't change that much. So, of course, the need arises because power outages cost, and that is attributed for the large part in our inadequate system understanding, which prompted the US, at least that I know, to invest a lot of money about 8 years ago, or 7 years ago for energy. And the Pennsylvania Act 129, even $1 billion in 4 years after the blackout hit them seriously. So the grid may share commonalities with the network, the communication network, but it has not changed as much, fundamentally, relatively speaking. If we look at this picture just to understand what is involved in the power grid, I'm trying to speak to people that are at least as clueless as I used to be 3 or 4 years ago on power. Although it has been deemed the most significant engineering achievement of the 20th century, if you take into account how much it has changed the lives of people. It consists basically of 3 parts, and I color code them here. On the left, we have the generation side. For the most part, crude oil or fuel of similar sorts. And then you have a transformer that changes the voltage up to match the transmission lines that are color-coded in blue. And then you get the transformer to step down the voltage and then serve customers. And you have sub-transmission customers, you have primary customers. You can see on the voltage here what they use. And you can have households and offices which are secondary customers. So, as I said, for the most part, the grid serves us well. It's reliable 99.9% of the time. But when something goes wrong, the cost is humongous. It costs at least 150 billion per year. So even that 0.03% is significant. And as time passes, people are more concerned with the environment and how to conserve and save it. And also they're thinking of how to engage all parts of the puzzle. So for the most part now, people look at problems that relate to the generation and the transmission. Now the emphasis is placed for the most part on the distribution level and the engagement of the customers. So, difficult to give definitions. What's a smart grid? You've heard the term. But one could argue that is an effort to advance this aging infrastructure with information technologies so that you can enhance the current electrical power network. That's a definition of the smart grid, or the grid of the future. And typically the adjectives that are associated with this are the following. You want it to be controllable. You want it to be resilient to cyber attacks. You want it to be efficient in consuming power. And this is what I was mentioning, that the customers, you want them to participate in the puzzle of the grid and have their own input. And you want to be aware of what's happening anywhere, and you want the grid to be green, and you want it to be self-restoring and be sustainable. So all these desiderata, desired features, you may ask, how can they become a reality? They will become a reality because technology advances at the same time. And if you want to highlight some things, power electronics become more and more efficient. I'm not going to talk about those too much because I know too little about. But sensors and meters, namely the power measurement units, are emerging in rapidly. For sure, communication networking can help this infrastructure in exchanging, either commands through smart meters or demand response messages or prices. And especially if you start, living in a city that has pollution problems, then the need for electric vehicles becomes more pronounced. But even in the sunny places like, Catalonia, the photovoltaics are technologies that we will see more use of in the coming future, along with wind. But I would argue that in order to collect the benefits of these technological advances, one needs to leverage tools that are more familiar in people in resource allocation, optimization, machine learning, and signal processing. So this is the tools that will bring together these advances to improve upon the aging infrastructure. So with this introduction, if you want to ask me a high-level question, but any level question, feel free to interrupt me at any time. Okay? This is the motivation for the talk. So I divided this talk into mainly two parts. One will deal, for the most part, with three parts, actually. These are basics of power system models. If you are a power engineer, you will be bored, most likely. But if you're not, I hope you will learn enough to move on to the next subjects that are monitoring of future power systems, and in particular the tasks that relate signal processing, controls, and machine learning. Then I will touch upon the optimal grid operation, and this includes economic operation, economic dispatch, and demand response. And I will touch upon briefly on electric vehicles and renewables toward the end of the presentation as well. So that's my plan: modeling, monitoring, optimization. Okay, so this is a good source if you guys are interested to. I think that we managed to squeeze almost everything in 15 slides. That you need to know from that book. But all right. So you can think of a power grid as an electric circuit, basically. And you have alternating current voltages, currents, and powers, which in steady state are sinusoids. Okay? So you have a sinusoid with an amplitude and a phase. And this is basically how power, voltage, and DC systems are also possible, but they're challenged by two things: the generation and the transmission losses. So it turns out that because you have rotating machinery at the generation, that induces by itself a frequency. So DC, frequency is not as easy. And actually, even on the transmission side, you can show that whenever you have AC, then oftentimes inductive and capacitive loads give rise to reactive power, and that basically can help lowering the transmission losses, okay? If handled properly. Pretty much like in communications, although we transmit at a frequency band, so we have passband signals, it is convenient oftentimes to multiply by the carrier and bring it down to baseband. So there is a complex representation that we use in analyzing communication systems. Pretty much the same can be convenient here. And these are called phasors. And the nominal frequency is either 50 hertz or 60 hertz. And so all of a sudden, all of these things become complex quantities. So you have complex voltages, complex powers, complex currents. So both coordinates can be used, polar. I will use the calligraphic notation to designate polar, and the Roman to designate amplitude. So whenever, because many times what you play with is the amplitude. I didn't want to carry all this absolute value around the presentation. So just remember V is the amplitude and theta is the phase. So the real and imaginary parts are also possible to use, rectangular coordinates. And let me start now defining quantities of interest for the grid. Let's look at, as an example, single phase equivalent. Remember, for reasons that also can be attributed to adding and subtracting and constructive and superposition, people many times like to transmit power in three phases. So, because you can facilitate removing undesirable effects with three phases. So here I show a single phase equivalent. That means you can call it baseband equivalent in communications. That's a single phase equivalent. So you have different nodes of a graph that you call buses. And these nodes can be either generators or loads. So you have generators, you have loads, reactive loads. So this is to represent banks of reactive power, you can call it, you can think of them as capacitors or inductors, collective inductors, basically. And this is a symbol for the resistance. So if you take all these nodes from, I don't know how many, I have 1, 2, whatever, 14, right? Should be 14. 14 buses, and you put them in a vector, right, V, then you can use this input-output relationship, which we refer to as Ohm's law, in a multivariate form. Clear? So basically it says, if you want to have only resistors, you remember that V equals IR is Ohm's law, right? So here I'm allowing myself for more complex level resistance, if you like. But this is the Ohm's law. So let's talk a little bit about the parameters of transmission lines, which for the most part tend to be considered as being time invariant. These parameters are line impedance, which is the superposition of resistance and reactance. The reactance is assumed to be positive, assuming that you have only inductors and not capacitors. So the admittance is 1 over the impedance, and it's also complex, signified by this G and this B. It's called conductance and susceptance. And it's clear that this rectangular form, representation of the complex impedance and the complex admittance, you can relate it using the polar form. So the G is expressible in terms of the amplitude and the phase of the Z. And because this X is positive, the BMN, the susceptance, is negative. So this is the celebrated pi model, where you have 2 buses, M and N, with corresponding voltages VM, Vn, and current flowing over the line. It has an admittance, YMN, and with the ground, it has a susceptance. This is the source of reactive power I was alluding to. So you have basically conservation of energy, if you like, because using these parameters, as you can imagine, you have that the voltage that traverses a line from bus M to bus N, IMN, is the difference between the voltages VM, Vn, and that's the red part, right? And also part of it goes down to the ground, right? So this is Vm minus 0, which is the ground, with a susceptance. So this is basically the IMN equals YMN Vm minus Vn equation. In buses, you also have bus injection currents. So I told you that, and this is the conservation of energy that I was alluding to. So the current that comes in bus M equals the current that flows out through all the lines Mn, where N is in the neighborhood of M, the connected versions. Is that clear? So now, if you write, remember what we had before, if you write the IMN, right, using the, you plug it, you plug this expression, or you put it differently. You take the summation of the overall Mn, so you substitute this formula from the previous slide, then you have precisely that the current in is expressible in terms of the voltages out and the line parameters YMN and BCMN. So if you now, remember, imagine now that you take all these node currents, injection currents, and you stack them in a vector, one under the other. Right? And likewise, you do the same thing for all the voltages. You stack them one under the other. If you notice, this equation is basically expressing that the nodal currents are linearly related with the nodal voltages, right? So if you construct this matrix YMN through the previous equation per line, then you get a multivariate Ohm's law. Now, remember what I said, the Y, every entry of the Y consists of 3 branches. It is either minus YMN, remember YMN is 1 over YMN is called the admittance, right? And it's 1 over the resistance, or the, so it contains all the YMNs from all lines other than the M, and all the susceptances to the ground of those lines. Now, if M is different than N, then it's just minus YMN, right? Remember, it comes from this fact. The minus YMN is the one that survives here if the M is equal to N. Is different than N. So of course, if there is no connection, in other words, between M and N, the entry of this bus admittance matrix is 0. Okay? Is that clear? So we will use it very frequently, this fact, that this bus admittance matrix, which plays a basic role for monitoring and optimization, is the matrix that literally captures the topology of your graph. It's supposed to be given. Every line, transmission line, has its characteristics. They may change if the weather changes extremely, but typically it's supposed to be constant. Okay? And this matrix in particular, you can easily verify that it's symmetric and non-Hermitian. And because every bus is not connected with many other buses, it is sparse. And this is something that can facilitate efficient computations and storage. Now, I want to also mention that you have the inverse matrix of the admittance matrix, which is called the bus impedance matrix. And this is what we saw earlier as being Z times I, just by inverting that. Now, if you take a matrix which is sparse, its inverse is not generally sparse. Is that clear? Because for every point you put the adjacency matrix, the adjoint matrix, then divide by the derivative. So this is non-sparse in general. Also, I want to emphasize that if you take the inverse, the entry of ZMN is not 1 over the little ymn, so which was defined as being the inverse of the impedance, of the line impedance. Is that clear? Yes?
Just one question here. When you present it this way, it means that it's completely deterministic and that at any time we know the value of resistances or admittances or anything.
This assumes that, yes.
Are there some studies on what happens if it's a sort of stochastic mobility in which those things are changing resistances with weather or whatever, and there's uncertainty on that, or is it good enough, the approximation that this thing is constant all the time?
For the most part, it is good enough, but this is just a model. We will see later on that there are cases whereby several parts of the network are not known deterministically, either because we don't have uh, uh, meters over there, or you cannot access them. These are called breakers. Sometimes you don't have knowledge on the control of breakers. And there, or sometimes you have line outages, right? So something goes wrong on a line, and in this case, you don't know it. But all I want to say is that in a variation, when we are going to study the state of the power system, the variations are not fast with the weather. So if you adopt an adaptive algorithm, the adaptive algorithm will be able to track the variations due to humidity changes, of temperature changes, and the like. So that's not the big deal. Okay. But outages are a big deal, and sometimes stochastic models, we will see what models are useful. Okay, good. So bottom line, currents are linearly expressed in terms of node voltages. That's all I told you. I told you basically Ohm's law and Kirchhoff's law. That's all I told you, and what is involved. You can think of Kirchhoff's law as a conservation of energy type of flow conservation in networks. Rate that goes in should go out, right? Same thing in queuing theory, a lot of fields. So this is basically its counterpart here. So since you have complex voltages and complex line parameters, the power is also complex. So it's called active, or the real part of the power, of the complex power, is the product of the voltage times the current conjugate. And you can write it in Cartesian form. This power is called, the real part is called the active power, and the imaginary part is called reactive power. You can think of reactive power, there are many ways to think of it, but you can think of it as being generated if a capacitor discharges. It can have beautiful effects, and constructive and destructive effects, if it's not handled properly, because basically it is generating a current with being out of phase relative to one that is being charged, right? So then it reacts to power. You can think of it as, you can think of reactive power as being the counterpart of resistance, right? In the imaginary part of the current, and it's the one that changes the phase of the current, basically. So the same way that, for example, you have resistances, and they resist the current flow over real networks, the reactance basically is a complex resistance. Okay, you can think of it that way. So over a line, similarly to nodes, we have the product of the voltage times the IMN. So you can collect these complex powers into a vector, which naturally it will be a diagonal of all the nodal voltages times all the line currents. I'm just writing this equation in matrix vector form. Is that clear? You collect all the SMNs, you multiply Vm times I. Now, remember, we have established the Ohm's law that relates the currents with voltages again through the impedance matrix. So what you can observe readily here is that we're talking about the quadratic equation. You have voltage and impedance, admittance. So in rectangular coordinates, you can write the impedance into capital G and capital B, and the entries of G have different values with the little g I mentioned earlier, and the entries of the imaginary part have different values based on the susceptance I defined earlier, to make all the notation self-consistent in matrix and vector form. Now, this is the most fundamental part of the modeling, how power flows. If you take what we defined here as complex power, and you equate the, along with GMB, which is the real and imaginary part of Y, you equate the real and the imaginary parts, you end up with these equations. You get the real part, which is the active power, right? If you only have resistors. Remember I told you it's quadratic, right? It involves Vm and Vn, okay? And because I has a conjugate here, right? So V has a conjugate here. You multiply V with its conjugate, and therefore you must understand that you're going to get the difference between phases, okay? So you have V and V star, right? So you have all possible differences. So what do you see here? You see that the active power is the product of voltages and the difference of phases with some parameters that depend on the topology, G and B. Clear? And likewise for the reactive power. What is the important observation here? That the power depends on voltage differences. Okay? That means unless I designate one bus with a known phase, I can never get the exact phase of all voltages from the power. Because you could always have basically, you understand what I'm saying, right? So if you plug, if you have theta m prime to be theta m plus an arbitrary theta 0, and theta n prime likewise, theta n plus theta 0, then it is obvious that the difference between the two prime quantities is the same, right? So both of them, you cancel the theta 0. So you can never, if I know the difference, you can never know whether you're theta m or theta m prime, right? So this justifies the reason that one of the buses is called the slack or swing bus, and without loss of generality, people set it up to be 0. Okay? Nowadays, with advanced meters like PMUs, you can get phases very accurately at different locations. But here, I'm talking about conventional power measurements. From power, you can only get phase differences. Okay? For the sake of completeness, I write the power also in the rectangular coordinates, which are also quadratic, but they are rarely used. We'll see some very recent uses of the rectangular coordinates. So what do you learn from that? If you learn 2, 3 things. How power is related to voltages, right? And the parameters of the network. You also learn that if you know the voltages everywhere, you can assess how power flows in the network, right? And of course, it tells you that if you know power, or if you can measure power somewhere, you can find voltages. You can look at them in different ways. If I know powers, I can find voltages. If I know voltages, I can find powers. Okay? These are perhaps the most important equations here. However, people have struggled, as you will see later on, with this quadratic dependence of the power into voltage. So they have developed useful approximations. And the first useful approximation they have developed is under these 3 assumptions. And the useful approximation number 1 is called DC flow model. The first approximation it makes, it assumes that the resistances of the lines are much smaller than the reactances. So we have lossless line. So you don't spend too much power on the line. So G in this notation is 0 because that's the inverse. So the angle differences are relatively small, and the voltages do not change too much. So without loss of generality, you can assume them to be 1 per unit. So you can assume normalized with a constant is approximately 1. If you do something like that, then everything is 1 here, observe. This one becomes BMN. The cosine becomes 0. And the sine of theta m minus theta m is approximately theta m minus theta n. So this is basically the first order linear approximation. Okay? Now, so you can observe here that if you do something like that, both the active power and the reactive power are expressed linearly in terms of the phases and the magnitudes, respectively, of voltages. Okay? So this model is called bus admittance model. I am basically repeating what I said earlier. And it is linearly shows the linear relationship between the nodal powers and the phase voltage differences. So if you take now all the nodal powers and you concatenate them into a vector, and you take these susceptances and you put them in a matrix form, where basically if things are equal, if you refer to the same bus, then you sum all the susceptances from around. Remember, this is a manifestation of the current in is equal to currents out. This is what gave us this approximation. And you get a bus admittance matrix, which is symmetric and positive semi-definite. Now, because the lines are lossless, so if you multiply with 1 transpose, you can demonstrate that this is equal to 0, which basically translates, if you multiply by 1 transpose from both sides, you can easily recognize that this is saying that the power across the network should sum up to 0, because every node, remember, can be either a generator, that means it adds power, or it can be a load, that means it consumes power. So this one tells you basically, it should not be surprising, in linear algebra we call it the null eigenvector, right? So the all 1 vectors is the null eigenvector of the bus admittance matrix. And intuitively, it makes perfect sense, because it's like telling you that as much power goes in the network should be consumed. Okay? That's basically what the positive and the negative. So a generator gets a positive power, a load gets a negative power, right? So if you put as much and you consume as much as you put, then you must have 0. So there's a beautiful, this B, the bus admittance matrix, offers a beautiful link of the grid, the power grid, as a graph. Okay, and this B is what is known in graph theory, the Laplacian of the graph. That is extremely important in a number of tasks, and we will see it also. That is very important in identifying outages in the following slides. So this completes my short overview of power system modeling. Let me take a minute to review what we have covered so far. So we said that the grid is like a circuit, okay? And there are AC and DC currents. AC is preferred over DC, or is natural. And you have one phase and multi-phase, right? Then we went on to talk about parameters of the grid. which are, you can think of them like resistors, inductors, and capacitors of a circuit. Okay? So every line has a generalized, if you like, resistance, and this generalized resistance is called the ordinary resistance and the reactance, okay, which is called admittance. And the inverse is 1 over that. Is also of interest because it enters in the Ohm's law and the Kirchhoff's law. And we saw that those are basically, can be written in a multivariate form because they involve a lot of currents in nodes or in lines. We mentioned that pretty much like communications, it is useful to look at things in a phasor form. And the phasor representation of voltages basically means that conveniently all important quantities like currents, voltages, and powers are complex numbers. Okay? You can think of them as being complex numbers. And finally, I introduce the power flow equations. After I talk 2 important laws, right? First important law is Ohm's law. Second important law is Kirchhoff's law. These are conservation. Current that goes in a bus equals the current that goes out of the sum of all the currents that go out of the bus. Okay? That's it. Then the first thing to remember is how power flows in a network. There are fundamental equations. These relate nodal powers, active and reactive, at each node, at each bus, with voltages and parameters. And in their AC general form, they are quadratic equations in the voltage amplitudes and depend on phase differences. However, these are nonlinear, second order equations. However, in certain cases, approximations are valid, first order approximations are valid, and these approximations allow us to look at power at nodes as the bus admittance matrix times a vector of phase differences. That's a linear model. Okay? That's all I told you so far. Any questions on the modeling? Yeah. No, here steady state for sure. Yeah. Yeah. Oh, yeah. It's actually, there is a reactive power management. See, reactive power is a power that's very flexible, so you can play with. And people have tried to use reactive power in order to what they call fill the valleys. Okay. The terminology is like this. Basically, operators do not like to see the power peaking frequently. So you want as smooth as possible. So they want the valleys to be filled. And then you can use reactive power there, which you can control. Because if you start saying, suppose you have a hydroelectric factory, right? It's very difficult to tell this person all of a sudden, boom, lower your consumption. They have these big rotors. That's how I envision them, right? So for them, it's very difficult to change anything in the generation. But at the distribution system, this is super contemporary research topic. A lot of funding is designated for how to use reactive power to basically fill the valleys of power. So use it to your advantage because it's flexible. The other is not as flexible. If I knew, I would, I publish papers. I publish papers on this theme, but I have so many. I try to follow a generic coverage. Yeah. Reactive power used to be bad, and it is bad in the transmission side, but at the distribution side can be used to your advantage. That's in a nutshell. So reactive power is the thing that, why it's the bad guy, because it changes the phase of the current. It generates current with different phase that is not aligned with your phase of the generated current. And that messes things up. So it lowers your, because when you add or multiply two signs with different, currents with different sign, then all of a sudden you may lower your, divide by 2 the actual power that you're transmitting. Okay, so remember what I told you? There is a relationship between power and voltage. And it's quadratic in general. In the approximation, it's linear. Okay? For many, many years, the most prevalent signal processing issue was this one, power system state estimation. At the very high level, it's as old as 1970. At a very high level, you are given meter readings and grid parameters, and you are trying to find the state vector V. Remember this power flow equation? It has P on the left-hand side and Q. And it has on the right-hand side some parameters of the network, the G and the B, and also the voltages. So we assume that we know the parameters, the grid parameters. We know so the meter gives you the left-hand side, and you're trying to find the voltages. Is that clear? So everything else, if you know the voltages, Mr. Ohm has told us how to find the currents, because if I know voltages and know the parameters, I can find everything, basically. This is, if you understand that, you understood the first basic thing of power systems. If you know voltages everywhere, you can monitor the system. You know what's going on, okay? Of course, you can imagine, you cannot have a voltage meter everywhere, right? It is very important for situation awareness. It's very important for reliability analysis and planning. It's very also important for load forecasting, because if I know the voltages there, even if I don't have measurements, then using in the reverse way the power flow equation, so I can tell you how much power is going to be needed there, right? If I know the voltages there, let's take a machine learning approach, data-driven. So a computer scientist does not care about models and power flow equations and stuff. It tells you, give me powers in the CTTC area over the last year, right? And predict what is the power in October 2016. I'm just exaggerating. Oh, let's make it easier. In October 27, tomorrow, right? What's the power demand in this building? Okay, then they will look at previous years and the weather patterns and everything. We'll build up a model, could be ARMA, autoregressive moving average, or it can have exogenous periodic components, whatever is your favorite. ARIMA is called in this sense. Then you can put the data down and predict what is the value of the power. So it is for that purpose. It's also for economic operations, and billing is very important. How much this region requires, and how do I expand the lines and this. So the first one who formulated the statistical problem was Schweppe in 1970. So let me give you the problem statement, and if you are in COM or signal processing, you will have an easy time now. So the supervisory control and data acquisition system, SCADA is the abbreviation, every 4 seconds sends readings or measurements to the control center. Now, the phases cannot be used because there are timing mismatches. This is among the advantages that the PMUs, the phasor measurement units, bring to the table. They are receiving from GPS stumps signals, and they know exactly the phase, and actually they measure not only power, but these traditional measurements, traditional meters, they measure only either voltage, voltage amplitude, or power, active or reactive, or power over a line, or reactive power over a line, or current. They don't measure. Remember, I told you, the calligraphic is the complex, right? The Roman is the amplitude, so no phases are measured. Okay? So, you take measurements like this, either a generator or a load here. I'm showing all the measurements here that you can get. You can get powers, you can get amplitude, voltages, amplitudes, and so on and so forth. You stack them in a vector Z, and you add noise. This H of E, because I didn't want to write the entire equation, which is quadratic, I know the equation is quadratic, but I denote it as H of V. So the state estimation problem for someone that can pre-whiten to make the noise white can recognize that the best thing you can do, the maximum likelihood optimum thing, if you don't understand what's maximum likelihood, don't care at this point, but you should know what Mr. Gauss said, least squares. Then basically the estimated voltage is the minimizer of this data fitting term. So you have the L2 norm of the error, Z minus HV, and you optimize over V. So, is that clear? What's the state estimation problem? You measure Z, which is basically power or voltages or voltage amplitudes, and you're trying to find voltages, the actual voltages, the complex voltages. Okay? There are a number of constraints you can impose. This is the plain vanilla nonlinear least squares problem. Weighted if you don't pre-whiten. So if someone tells you, you know what, this is a generation bus, so you should say that this guy is generating, so it does not receive anything from others, so the injection is 0 of the PMQM. Or someone may tell you that, you know what, I know that the amplitudes are between a range, so I can put that as a constraint as well. So the question is, how do you solve this problem? It's nonlinear least squares. The typical way of solving it, the method 1, and a lot of papers have been published around it, is to use a first order approximation around a linearized value V sub k. So basically you take the nonlinear function, you approximate it at point Vk, and you keep only the first term in the Taylor expansion. And this basically, if you linearize this HV with this guy, allows you to have a closed form expression where Gk is the Jacobian of the transformation H at Vk. So in a way, this amounts to a gradient descent type of approach, whereby Vk plus 1 at k is now the iteration index, I hope. It's clear. Vk plus 1 is Vk, and the correction of this error term. So a number of variants using Cholesky factorization for numerical stability, because the inverse can be problematic. You can have diagonal loading and the like. So what's the problem? The problem is that this is sensitive to initialization, because you have a nonlinear least squares, and there's no convergence guarantee. So other people have used to approximate this inverse with the flat profile, voltage profile, and so they don't evaluate it at every point. So they keep it constant. But the truth of the matter is that up until recently, people were using these Gauss-Newton iterations to solve the quadratic system of equations. This was the time that we came into picture, and basically we made a recognition that is well known in optimization, but power system engineers were not aware of it. So if you go to the rectangular coordinates of the complex power and you rewrite, you use the canonical vector of all ones, except for them all zeros, with the mth entry to be 1, right? So this EM times V is a vector that with the inner product isolates the mth entry of the V, right? And likewise, on the right-hand side, we isolate the mth entry of the I. But remember, the I from Ohm's law is Y times V. So what you can write this scalar form using the trace operator in this way. So you can move the basically the EM on the right-hand side and the Y on the other side, and baptize this matrix H of M. This matrix depends only on the topology of the grid, and then write the voltages in an outer product form. This outer product form allows us to define a matrix, a rank 1 matrix V. So instead of the classical nonlinearly squares, we wrote it in a form that is linear in the matrix V. So you are nonlinear in the vector V, but you are linear in the matrix V, which is rank 1. So you have the constraint that V must be semi-definite and has rank 1. You have not done anything to change things here, but if you use the common trick of dropping the rank 1 constraint and reinforcing it at the end, then you have a convex problem that you can solve with near optimal solvers, regardless of the initialization, at complexity that grows polynomial in the worst case, 4.5, depending on the accuracy that you want to achieve. So this semi-definite relaxation was first used for state estimation in our group. And before us, there was this gentleman that used it for optimal power flow. And after us, the Caltech group used it also for optimal power flow. It is possible to generalize it to include PMU data, measurement units, and you can robustify the semi-definite relaxation whenever you have outliers and bad data. All right, so let me demonstrate to you how important this major advance is. We have filed a patent on that, and apparently there is major possibility for success. But here I'm showing with numerical tests how the weighted least squares performs. This is the angle error. You find the phases because the amplitudes are fixed to 1. And then the angle error of the competing alternative is the red. And you see that it exhibits huge errors in degrees. And we are definitely closer with the blue line. This is our method, the semi-definite relaxation. And if we use the semi-definite relaxation as an initialization for the weighted least squares, you can improve even further. So in addition to static power system state estimation, people have looked into dynamic alternatives. And to this end, they have introduced different models to capture the dynamics of the voltage variation, which could be either a random walk model or one with exogenous load, and you are given measurements ZT, which are again linear quadratic, and you can use the extended Kalman filter using a prediction corrector form. This is the standard thing that you'd use in tracking systems, and advances of what they call uncentered Kalman filter, but where you get improvement in accuracy but less complex, increased complexity. And even particle filtering has been used if it is affordable by real-time requirements. Now, so remember what is power system state estimation? I want to find the voltages everywhere, right? I know them. I know the powers somewhere. I want to find the voltages everywhere. Now, in the past, there was no guarantee that you will converge to the global optimum. And since there was an extreme sensitivity on initialization. Why? Why this is very difficult now? If you start integrating renewables, wind, and these things change with time. There is a stochasticity involved. So the initial condition that you use to initiate your Gauss-Newton iterations may change after a while because the voltages have changed dramatically. So being able to have near optimal performance is very critical. So we managed to do that using the semi-definite relaxation trick. But if you noticed here, the polynomial, the complexity is not innocent. Is n to the fourth, even in the worst case, which means that if you have a huge network that you're controlling with thousands of nodes, that is not advisable to use or not as attractive. So there is a need to develop decentralized approaches to power system state estimation. Of course, this comes at a very interesting investigation, because in addition to being scalable with a control area size, you want to remain private. So different operators or aggregators or estimators of the power system state may not be willing to tell you what their voltages in their own areas are. So let's take for a toy example here. We have four state areas, area 1, 2, 3, and 4. So if you look at area 2, for example, it has buses 3, 4, 7, 8. But it also has a tie line that connects 7 with 9, 4 with 9, and 4 with 5. So you can define an extended area 2. One approach is, if you want to be purely local, is you ignore the tie lines. You forget about this. I forgot to say in this, the blue boxes are meters, right? So whenever you see a blue box, that means you're measuring whatever you need there. So one approach is to ignore these tie lines between areas and perform your own state estimation within every area. Of course, this is statistically suboptimum because you don't get information from measurements on other sides, right? So if, for example, this guy 1, 2, 5 ignores these tie lines, does not get measurement from, does not benefit from that measurement there. Also, look, for example, at area 4. If area 4 cuts its measurement, it does not know what's happening at bus 11. So you lose observability if you cut the tie line, the connection. So if you want to go purely local, then you lose observability. So that is a second option that I refer to, is to augment every area with the lasso lines of the same color. So for the green line, look at the lasso line that includes 9 from area 3 and 5 from area 1. So basically the idea is the following that we came up with. If possible, try to solve your local problem, but the estimate that you find about the voltage 9, you exchange it with the area 3 operator, and that for bus 5, you exchange it with area 1 operator. So to make the long story short, let's look at the semi-definite relaxation approach. So you take the least squares cost and you split it on a per area basis. The L index is the index of the bus within each area K. So MK is the number of buses in area K. Actually, I will use neighborhood 2 for area, augmented with 5 to signify the augmented one with a parenthesis at 2. So let's look at what happens with the original problem. The original problem says sum overall areas, sum overall buses per area, and maintain the positive definiteness of the matrix V. Now, the point is, if the neighborhoods overlap, the positive semi-definite constraint couples the voltage submatrices. Okay, here is what happens. So these voltage subspaces, voltage V sub K, are submatrices of the big matrix V. So if you have overlap, then you have a hope of rendering local estimators global estimators. On the other hand, there is a challenge that if I have a positive definite matrix V, this is not necessary and sufficient to have overlapping submatrices positive definite. The other way is around. If I am completely decoupled, I can solve every system and have positive definiteness, and the entire will be positive definite. But if there is overlap, this is not guaranteed. So the overlap is a blessing, but it's also a challenge. It's a blessing because it helps you to convey information from neighboring areas to your area. So we demonstrated that there are, I don't want to go to graph theoretic details, but most distribution networks are radial networks. That means they have a root. It's like what we call tree networks in graph theory. It's like a tree. What we have proved is that if your network is a tree, then there is no penalty in decentralizing it. So if you include the tie lines and you enforce positive definiteness in the extended voltage matrices, and you demand the voltages shared, the bus is shared to have the same estimate, then by solving the decentralized per area state estimation is equivalent to solving the global state estimation. Okay? And for that, we have used the alternating direction method of multipliers. That is a popular method. It was developed in the optimization circles in the 70s, but it was first recognized that it has merits for distributed estimation using sensor networks at the beginning by our group back in 2007. So basically, I'll give you a pictorial high-level description. What happens is you have this optimization, these constraints, You associate Lagrange multipliers with every constraint. So every area gets Lagrange multipliers from the neighborhood, runs a local SDP, semi-definite program, and spits off voltage matrices that contain the estimates. Now, it sends only tie line estimates that are received by neighbors, and those, again, send off Lagrange multipliers that are linearly updated. We have shown that you can prove convergence of these iterations, as I is the iteration index, to the centralized solution, even when the links are noisy and asynchronous, which is quite possible if you have lines drop. So let me show you here how the alternating direction method multiplier works. So here I show the local matrix error versus iteration index for the 4 areas that are demonstrated here. So what you see here is that for different areas, after even no more than 100 iterations, you get back to the 10 to the minus 2 or 10 to the minus 5. And this is a real test from an IEEE bus standard. It has 3 areas. What you want to notice is that these tie lines have flow meters in all lines except 23, 24, and this one makes it to become a tree. And the graph areas behave like a tree. And if you want to draw analogies, and you are familiar with communications, you know that whenever you do message passing, you don't like the nodes to have loops. This is somewhat analogous to that. So if you don't have trees, if you have radial networks, then you can prove that the centralized can work as well as the centralized. And as you see over here, the 4 areas, this estimation error of their voltages vanishes with iterations. Rather, this demonstrates basically that they approach the centralized solution within 20 iterations. Now, moving on to PMUs. PMUs are very good because they provide linear models. Because as I told you, PMUs in essence, in addition to power measurements, they can give you currents. And by measuring currents as well in complex form with their phase, in other words, you can go to the Ohm's law. So you have some linear dependence with the voltage. So you don't have to face the trouble that the conventional meters have. On the other hand, PMUs are not by any means so cheap. I mean, more than thousands of dollars to install in each and every house or each and every premise. So it's a good idea to have things that can combine both. But in certain critical parts of the network, of the power network, you can deploy PMUs to give you reliable information about the current and therefore have a linear model. But still, even in this case, you want to minimize the least squares cost. And basically, you can have that the problems are coupled. I denoted X to be the voltages again here. And you can use the method of multipliers. Here, basically, the cost F can be the quadratic cost or something else that we will see shortly if you want to have robustness. And the P acts as the Lagrange multiplier, which tells you how far the 2 areas that are neighboring are away from consensus. So if this is like a prior information that drives you to consent on the shared variables. So for example, if you use the quadratic cost, these iterations can be solved in closed form using least squares. Actually, it's like the least squares with Tikhonov regularization, that you get from your neighborhoods, the neighboring areas, and this one describes the Lagrange multiplier update. What is very important to stress is here a plot which shows the mean square error of the voltage estimate versus iterations. And here is from the CMU group, this is the mean square error of the difference between centralized and decentralized. The problem is not that they do not, in their problem, they did the somewhat unrealistic approach to take a consensus algorithm and consent among the voltage vector that contains all voltages of the entire network. So they may end up having, thousands of variables per vector. And that's not it converges very, very slowly. And eventually, if you wait until thousands of iterations, you may go down. But in the first 50 iterations, that's how bad they can be. And the difference between decentralized and centralized in our case is obviously down to 10 to the minus 8 within 50 iterations. So I mentioned basically that there is a possibility of having outliers, either intentionally by cybersecurity threats or because you have malfunctioning nodes. So these manifest themselves into a variable O. O stands for outliers. So the X is your desirable variable. You do now a least squares cost. Oh, first of all, if I want to estimate X and O, it is clearly, I'm running out of equations because the number of equations is as many as the number of entries in O, right? So if in addition to O, I have unknowns in the X, then I cannot solve this, an ill-posed problem. However, what saves me is the fact that the outliers tend to be few. So if I have 1,000 buses, I don't expect someone to go and do something wrong in all 1,000 buses. So if my outliers are, actually, the bottom line is that the outliers is sparse, right? The outlier vector is sparse, this vector. So if an outlier is not sparse, then it's a nominal, it's not an outlier. So you can reveal single and block errors if you regularize your least squares cost with your L1 norm, which is known to promote sparsity from compressive sampling signal processing. So this is what and actually you can prove that this is identical to the Huber cost function that is known to penalize. I don't know how many of you have heard about the Huber cost function. If you have not heard, basically, if you have least squares, if you have a cost function of then per datum, you're trying to minimize the least squares cost. But if you know that all your errors will be from minus lambda up to lambda, then you could basically forget about, you can do an objective function that are like this, right? But what's the problem of this objective function? Non-convex also, in addition to not being differentiable. Is non-convex. So Mr. Huber basically said that a smart idea is to, because the quadratic is too fast increasing, to take the tangent at this point and have a linear increase. So basically, this is much better than the quadratic that penalizes errors. And you know what's the problem with outliers? For those of you that have not heard about, right, if you focus on the problem, let's say, of line fitting, right? You know what happens. If someone gives you measurements y, x, right? And most of the measurements are around here. Then it doesn't take too much to believe that a line that behaves like this will do a good job to fit these things. But if all of a sudden you get some measurements here, here, 2 of them is enough, right? If you do least squares, including this and this, then you may end up having a line like this, because these are very far. So you're trying to, so, but whenever you use the absolute value, in the error, you have much better hope to suppress the outliers. Okay? So that's what's happening here. So the good news is that you can decentralize any cost function the way I just described it into different areas. So you can iteratively solve for the x and O. So when you solve for x, you treat O as fixed, and you update x in closed form using the formula we showed earlier. When you freeze x and you solve for O, you freeze z minus hx, and then you have a soft thresholding operator. So if it's outside that region, you give it this plus value or minus value. Or inside the region, you throw away that measurement. And then you update using an LMS-like update your multiplier to tell you how far you are from consensus. And likewise, this one shows the least squares and distributed robust PSSE. So you see very well that these are basically after 8 iterations, they converge to the centralized solution, the least square solution. Well, if you give me 2 slides, if you give me 2 minutes, I will just cover I finished the state estimation problem. And this will bring me to the question that one of you asked me earlier. The power engineers call this generalized power system state equation. The previous is not Cabnou, is a major, I'm trying to remember, it's a football, American football. And where, I don't remember, I think it was in Philadelphia, the game. But it was a major game, final. And for more than an hour, half of the stadium was in dark. And it was a major loss, and even that half hour. And later on, they realized that it was because some circuit breakers were burned, and people did not realize them. So that creates the cascaded effect that killed many lines, one after the other. So let me tell you now what happens really. Sometimes, although whenever we have a bus and branch model, we basically look at even one building or one stadium as one node, or parts of the stadium major power consumers as one node. But actually it's not one node. Every node has a section. So for example, it has a number of switches, if you like, that are called the circuit breakers. And they're used for protection and reconfiguration. So for example, if it is closed, there is no voltage drop. So the voltage 15 is the same as the voltage 16, all right? And if it's open, like here, no current flows through it. And sometimes you may do it in order to protect something, a circuit breaker. If you had a good circuit breakers and you know that something has gone right, then you can switch. And it's like a way of changing the topology of the network. So if I switch pieces here and there, then I can make the power flow differently, and then I can save things that are not designed to handle so much power. Okay? So this goes back to your question, where this way the parameters that I have shown earlier can be altered. So one way of modeling that, and this is what we came up with a couple of years ago, is to use some of these circuit breakers are instrumented, so you know what happens there. So the system operator knows, or the control system knows what's happening. And some of them are uninstrumented, so you don't know what's going on. So what we proposed is to do the following: to include the voltages in the X, real and imaginary part, and also the power, real and imaginary part, and or the currents, and the power actually, and then the C times X equals 0 basically tells you, implements the instrumented buses. So this C, we know exactly, it's a plus minus 1 entry type of, it has plus minus 1 and 0. These are the entries of the C. And they implement all those equations in the entire network. Okay? So it acts as a constraint. But the ones that are uninstrumented, then we have the topology in the selected buses that we're suspecting to have a problem. And then we try to solve this minimization problem, whereby we say that I want to match the measurements I have. I know this should be instrumented and they behave that way because I see what the measurements. And those that I don't know, basically I put them as a constraint for the system of equations to tell me which one is on and which one is off. So it is an effort here to do simultaneous estimation of voltages and suspected parameters of the topology. So you asked me earlier, are these, all of them, known? My answer is not always. But you can include some of them as being unknowns in your state estimation problem. So although traditionally state estimation has been developed in order to estimate voltages, and we have seen that estimating voltages allows estimation of everything, okay? Sometimes it is important and challenging to look also into generalized state estimation problems, where you also estimate the topology of the power network. Yes? Huge. The impact is that if you don't know what's going on, you have cascade failures one after the other. So the impact is huge. Let me say two things. I don't know if I got them through. The problem in its full form is non-convex in the AC form. If you have power measurement units, you can have linear measurements. And that saves the day. So you can actually incorporate, I didn't show it, but all these papers that I cite under the SDR, they consider joint costs of quadratic measurements that have nonlinear squares and linear measurements like the one that I showed, what did I do? Here. Linear measurements that I showed here, right? Remember? Yep. Here the measurements are linear. And they are linear because the PMUs, remember at the very beginning, I showed some new measurement units, new smart meters. These are the PMUs. I'll talk a little bit more about PMUs. But PMUs, for your purposes, are, if someone goes out, asks you tomorrow, what is a PMU? A PMU is a box that can measure currents. It samples 1,000 times faster, the system. So instead of having one measurement every 4 seconds, that's the current meters. Right now we have, every millisecond, almost. So that level. And you can get the phases also, because you have the timing. They are time synchronized measurements. Okay? So you know how the phase of the sinusoid evolves. So this is, but they are expensive, the PMUs. But to complete the story, indeed, quadratic measurements are useful because we have power meters in our homes. And we have to do something with those. You can get help from PMUs, or you can get help from semi-definite relaxation that allows you to treat it as linear. That's what we did, basically. And you can decentralize it. It's extremely important because with the deregulation, the industry is going to become much more active the moment we start splitting the market. We will see it later on in the optimization aspects of the grid. So there are a lot of entities that pretty much like wind and, all the operators that we have in the telephone system, independent system operators who will be split and try to claim customers in different neighborhoods. And that encourages a lot decentralized solution. Nobody's going to tell you, because I don't know whether you know that, but there have been papers that demonstrate what you're doing at home just by judging the power profile of your home. Because you know that every device in your home has a different signature in power. Even just to, people have been monitored to watch, prohibited movies overnight, and they know exactly the box, how much power it consumes, and so on and so forth. So they can know almost everything what you're doing. So that's why they don't like to exchange. If they tell you, that's my voltage profile of this guy over the last week, then somebody else is going to do something to you, will try to attract you, and so on and so forth. There's a lot of such games that are being played these days. So back to your question. Yes, you can have approximations to the optimum non-convex solution. And if you can combine conventional meters with linear measurements acquired through PMUs, you can even have global optimum claims.
So it's not acceptable estimated statements, not the real one, because then the control that will be made will just mess up with the system.
Believe me, if you remember the power flow equations, everything depends, and Ohm's law, everything depends on voltages. And another thing that I didn't tell you, that I didn't touch too much about it because there's a lot of deep theory behind it. You can ask yourself, I have a network, right? What is the minimum number of places I need to measure to establish identifiability? Because I cannot measure everything, right? So where can I measure them? So this is called observability, right, of a network. So that's also another issue. Because there might be cases, I showed you that even if you don't have one link, you may lose one area. Because one bus, you don't know what's going on there. So everything is interdependent. So the moment you lose voltage measurements, you're doomed to fail. I want to take a break soon, so I want to go over to that point. I think that's a good point to break. Yeah, I think this is a good. If you want to take a 10-minute break, we can do so. What do you think?